All right, everybody, welcome to another IAEI News Live. My name is Tom Dimitrovich, and today we're going to talk about a little bit of a technical topic, but a technology that you'll probably see in the field at some point installed on power distribution system equipment. And I would argue that many do not understand the ins and outs of this technology. So we're going to talk about zone selective interlocking, and it all starts now. All right, welcome back. And yes, this is another IAEI News Live, and it finds me out traveling a little bit because, getting out to see people and experience and have discussions, break bread with each other, that's what brings, and I think that's the glue of our electrical industry, and that's how we learn. So I firmly believe in a healthy mix of online and in person is a good thing. And now that things are getting back to a new normal, I would argue, you've got to start looking for your next IAEI event local to you in your location. So you got to get out to the IAEI's website, look for the educational opportunities. You're looking for a chapter meeting, a division meeting, or go to one of the IAEI section meetings. And you'll have a great opportunity to talk to people about electrical safety, sharing the passion around the National Electrical Code or other important documents like NFPA 70E for safe work practices, 70B for maintenance, NFPA 110 and 111 on your backup systems, NFPA 99 for healthcare. There's 72. There's so many technical topics that we can share our knowledge about and engage with those that we meet at these IAEI meetings. You'll find a wealth of information. So leverage that. Leverage your membership as an IAEI member as well. Get out there to the website, log in, and you can connect with your fellow friends and others who might be on code making panels that you can engage with directly on the IAEI's network. So, but first, we're here to talk about a technology called zone selective interlocking. Now, zone selective interlocking is, and I say it's a technology that unfortunately many people don't quite understand. I've heard some people refer to zone selective interlocking as the way to achieve selective coordination. I've heard people refer to zone selective interlocking as circuit breakers communicating with each other, and there's a communication network that helps improve the reliability of the power distribution system. Sometimes people get things sort of skewed a little bit, and sometimes they nail it right on, but I don't think they quite understand exactly what zone selective interlocking is. So our discussion is hopefully going to try to clarify a little bit more around this technology. Now, I will say, zone selective interlocking has been around for quite some time. I remember when I joined my organization, when I moved from an architectural engineering firm where I was working on power distribution system analysis and design. I was doing short circuit studies, coordination studies. We were changing motor control centers out, revitalizing and refurbishing buckets and all this good stuff, taking out the old and putting in the new technologies. And this was 1996 when I joined my company that I currently work for, a manufacturer. And in 1996, I worked with customers employing technologies like zone selective interlocking. So it's not something that's new. Zone selective interlocking is far from being new technology on the market. Zone selective interlocking is a technology that's been around for a while. And I'll tell you, at the heart of ZSI, meaning being the first letter of each of these words, is equipment protection. The goal of zone selective interlocking is to provide equipment protection, reduce the damage in the equipment within which this technology is employed. Now, the primary goal, and if you think about back in '96, and again, this technology was around before 1996, before I became aware of it. Okay, but even as a consulting engineer at the time, I was not aware of zone selective interlocking and what it can provide, and from a protection perspective, or reduced equipment damage. And what we know now as arc flash, but we did not know it as arc flash back in '95, because why? The document that we use to calculate the value of incident energy, or to put a value, a number to an arc flash event, that document is known as IEEE 1584. You can search it on the web. IEEE 1584 is the reference that we use, and it's the primary reference. There are other references, don't get me wrong, but it is the primary reference that we use to calculate calories per centimeter squared. Now, remember I said arc flash, zone selective interlocking was around before we knew what arc flash was. I mean, we knew what an arc flash was, but we didn't have a way to calculate those values at this time. So it wasn't until 2002 that document came out that helped us quantify that, but everybody was talking about this. But zone selective interlocking was typically employed to reduce equipment damage. Now, if you think about a piece of it, I'm going to try to simplify what I'm talking about. And if I think about a piece of equipment that has a main and feeder breakers, right? When I employ zone selective interlocking in this type of an arrangement or this type of equipment, I'm protecting what's in this box. I'm protecting what's inside that enclosure. And I'm doing that leveraging the overcurrent protective devices. So I'm going to throw another term out to you, and we'll call it differential relaying. Now, if you're familiar with what differential relaying is and differential protection, you may or may not understand this, but I always call it when he was talking about the gazintas, right? And what differential relaying does, you strategically place current transformers within a power distribution system piece of equipment, or around a transformer, around anything. And whatever current goes in has to come out. It follows back on the basics fundamentals of circuit theory. A series circuit, you know that whatever current goes into that circuit has to come out of that circuit. So differential protection means the principle that it operates off of is that if I have, for example, if I look at this one-line diagram and I look at that main breaker, if I see 1,000 amps go into the main breaker, and I have 333 amps going through each of those feeder breakers or branch breakers, and whatever, if I have 1,000 amps going in and I have 1,000 amps going out, added up across those three circuit breakers that are downstream of that main, then what goes in equals what goes out. Hence, all of the current is accounted for. So in differential relaying, the challenge with differential relaying is you have to employ a lot more technology. You have to have CTs. You think about this circuit. Think about this circuit. You have I'm showing a single circuit breaker on each of these lines, but in reality, there's 3 phases. You have A, B, and C. And if I'm going to employ current transformers, I need a current transformer around A, B, and C. So I need 3 CTs for the main breaker. I need 3 CTs on each of those feeders and branches that are downstream. That adds up to a lot of CTs, a lot of wires. And if I wanted to do differential relaying, I would need to have a relay in addition to those CTs, because the CTs would have to all go back to that relay. Think about the complexity of what we're talking about. Now, the invention, at some point, we've had relays for quite some time, electromechanical relays. And a lot of those were discs that moved. Those were very mechanical devices. You had current transformer sensors. Well, at some point, someone invented what was called the circuit board. And what did they do? They put that circuit board inside of a circuit breaker. These little trip units that are on the and built into a circuit breaker, just like this here. So you take a device like this. This is a trip unit for a, say, power circuit breaker or an insulated case circuit breaker. Now, I'm showing a trip unit like this, which would be on a power breaker or an insulated case, but I could have this a trip unit that doesn't fit this form factor, but it is smaller and fits into a molded case circuit breaker. So now I have an electronic brain inside of a molded case circuit breaker. So the engineers who built these devices and who put the brain inside of these circuit breakers realized they've got a microprocessor. And they realized that, look, if I'm going to employ differential relaying, then I am going to have to put all of these sensors in, and I need to have sensors, I need to have relays, and at some point it becomes, at some point in the system where you have a piece of equipment that is getting lower and lower in cost. The cost of the technology is going up and up and up, and at some point they're going to cross, and you may not have any payback because it's probably cheaper just to replace the equipment than it is to try to buy the technologies to protect the equipment. And you say, you know what, if there's a problem, then I'm just going to replace it, because the cost of everything to prevent the damage doesn't give you a return on investment, right? And remember, this is before we started thinking about, we've always thought about the electrical worker, but in reality, if you think about it, these technologies weren't employed to protect personnel. These technologies were employed to protect large equipment that costs hundreds of thousands of dollars, so that you didn't have to replace them if you had a problem inside the equipment. So, fast forward to these electronic devices, these trip units with a brain, and the engineer on these products said, we've got this powerful brain that we can program to do certain things. And we can take that very expensive, complicated differential relaying system and use the brain that is already in each of these circuit breakers. And think, built into each circuit breaker are sensors, the CTs that you would be putting in externally. Now they're built into the circuit breaker. Even the small molded case circuit breakers have sensors, those CTs. So you're not field installing CTs. And the relay, it's in there. You don't have to put a separate relay. So you've got a microprocessor that is more powerful probably than what put us on the moon inside of every one of these circuit breakers. And the engineer on that project said, I can make a system that leverages this technology and replaces a differential relaying scheme. And that is how zone selective interlocking was born. It was born out of technology growth and what was being placed inside of these circuit breakers. So you have a extreme technology growth, and it was pretty fast, relatively speaking. In our electrical industry, things don't change quickly. And when they do, we all get nervous. Think about it, right? We're an industry that's technically changing, but if you think about, iPads and all of these digital hardwares and where cell phone technology and that world has gone in such a fast period of time, our industry does not change as fast as those technologies do. And some of that is good, because this equipment, when it goes boom big, right? And it can hurt people. So there are reasons why we are a little bit slower to move on certain things and certain technologies. We want to be cautious, we want to be thorough, we want to make sure we don't have that unintended rapid disassembly in the field. Okay, so now if you think about zone selective, think about differential, the concept of differential relaying. What goes in has to equal what goes out. Very similar here. Very similar, not exact, but very similar. It achieves the same goal. So when you think about a protective system, you have a main, all of these devices are physically wired together. Now, some people will say, well, that they're communicating. You're putting basically a twisted pair between each of these devices. You're connecting them together. And I'm just looking to see if in this document here, because every manufacturer is going to have a different voltage signal that is provided. And I gotta see if it is in here. So we wire a set of twisted pairs. They don't need to be shielded. Shielded twisted pairs are used for communications when you're doing protocol work. All we are doing with this system is we're basically looking for the presence of a voltage. A very low DC voltage. And in some cases, one manufacturer may pick a certain voltage level that they're looking for, and another picks a different voltage level. But the key thing is that you're pulling wires between these circuit breakers. Each of the downstream breakers has to be wired back to that main breaker, that one upstream. And then what happens is, I'm looking for that number, and I know it's got to be in here on what at least one manufacturer uses. And for the life of me, I do not see that level of detail in at least this one document that I'm looking at. Here we go. Plus and 5. So in this case, they're looking at 5 volts DC. Very low voltage. I've heard of people using 24 volts DC, but we're looking at nominal input voltage plus 5 volt DC. Maximum is 5.5 volts DC. So the signal is very small, but it's a DC voltage. So I am physically wiring small conductors to terminals on each of these breakers, and I'm pulling them from the downstream to the upstream. So that's the physical nature of it. Now, I'm going to walk you through how they actually talk to each other. So when you think about a circuit breaker, you've got to understand that a circuit breaker, when current passes through the circuit breaker, it has a trip curve, right? So circuit breakers have trip curves. And at some point, when the current gets high enough, think about that circuit breaker's got a brain in it, and it's watching current pass through it. It knows the value of that current. It's sampling that current in cycles, subcycles. So it's calculating an RMS value. It'll know your peak values. It knows a lot of information, and depending upon the trip unit, you can get a lot of other additional information that is not necessarily needed for ZSI. But the sampling rates will dictate what you can and cannot provide from an information perspective. The granularity is what you're looking for. Now, okay, so if you think about each circuit breaker has a trip curve. And the trip curve looks a little bit like what this is. And this is, when you see a trip curve that has these straight lines like that, you know right off the bat there's an electronic trip unit in there, because a mechanical device is not going to have a nice clean lines like this has. Now, when from a TCC perspective, a time current characteristic curve perspective, you know that you have different pickup points. So in fact, I'm going to just draw something here. So one pickup point is right in this area. That is what we call a long time pickup. That setting is what provides the protection for the conductor. So if I have 200 amps worth of conductor, and when I say 200 amps worth of conductor, remember, I've got to do my ampacity calculation based on conditions of use, right? And I'm going to do all the math. I'm not going to get into the details of that, but I'm going to arrive upon a number that I say I have 200 amps worth of conductor. It can handle 200 amps every day of the week, twice on Sunday. That top portion of the trip curve provides the overcurrent protection for that conductor. Now, as you move down in this trip curve, you get into what we call this first little knee right in here. That is the transition. You are moving into what we call the short time delay. Now, you'll notice that there's a delay time period in this area here of the trip curve. And the reason that delay is there is to let the devices downstream clear faults without taking this device out. And we call that selective coordination. So whenever you install circuit breakers in the power distribution system, you're going to make these adjustments. You're going to establish what the long time pickup needs to be. And this portion of the curve right up here, that's called a long time delay. And typically you can move that long time delay up and down, right? I can move it up and down like that. So I can have a longer delay or I can bring it down, and it'll have an adjustability range on the face of the trip unit. That has nothing to do with the ampacity of the conductor. That adjustment is just around selective coordination. I don't want to, if I have a fuse upstream or another circuit breaker, say I have another circuit breaker that comes down like this, upstream, and right here, I'm bumping into that knee, I might have to move my long time delay of that downstream circuit breaker down to selectively coordinate with an upstream circuit breaker. That's the only reason you're moving that portion of the curve. It has nothing to do with the level of protection for the conductor. You're covered with that long time pickup. So now I've established this area up here of this trip curve. So now let's talk about this area down there. That is what I would call my short time delay. And why would I need a short time delay? If for some reason I want to add an intentional delay, so maybe I have a fuse that does this. And I'm not good at drawing fuse. But what if my fuse curve did this and I need separation? So I need an intentional delay of my upstream overcurrent protected device to let the fuse open downstream while I keep the circuit breaker's contacts closed upstream. That's what we call selective coordination. This is what a coordination engineer will do. A coordination engineer will tell you what this setting needs to be to protect the conductor. They'll tell you what this long time delay setting needs to be for coordination with upstream and downstream devices. They'll tell you what the pickup value needs to be of that short time delay. And then not only the pickup value, whenever I say pickup, I'm talking current. Whenever I say delay, I'm talking time. So when I say pickup, that is a moving that curve left and right. I can increase the pickup, meaning it takes more current to get into this region or less current to get into this region. And when I say a time delay, that is taking this portion of the curve and moving it up and down. So I can add delay or take a delay away. Make sense? And why am I doing any of that? For selective coordination. Now, I will say that all of that work that you do for selective coordination or coordination, whatever you want to, whatever level, degree of selectivity that you're going for, whatever set points you need to achieve that goal has nothing to do with zone selective interlocking. I'm going to say that again. All of those set points to achieve your coordination or selective coordination goals of moving that trip curve all around to accommodate upstream and downstream devices has nothing to do with zone selective interlocking. Not for the instantaneous, not for zone selective for ground. If you're using zone selective interlocking and selective coordination in the same breath, you're not understanding zone selective interlocking. Zone selective interlocking is there for equipment protection and arc flash reduction. That's what it's there for. It's not there for selective coordination. You have no idea how many people get that wrong. No idea how many people get that wrong. Now, so now you know that when I have a setup like this, for example, and I have that main breaker and I have those feeders, whatever I need to do for selective coordination, my engineer or your engineer is going to coordinate those, tell you what the settings need to be. And you need to plug them into the trip units for these devices. Don't say, I don't need to worry about that in the selective coordination study and plug those values in because I'm zone selective and interlocking my system. That would be ungood. It would be technically inaccurate, right? You've got to focus on the settings to achieve your selective coordination goals, and then you're going to focus on the equipment protection if you're employing zone selective interlocking. All right, so now those are going to be wired together. Now, here's basically what's occurring in a zone selective interlocking system. The main breaker is what does the work, and your basic principle is that you are either going to tell that main circuit breaker is either going to wait based upon the settings that you put in to achieve your selective coordination or any level of coordination that you've gone for it. It's going to follow the trip curve based on the settings that you have plugged into that trip unit. That's option one. And if it's not doing that, then it is going to ignore all of those settings that you put in and trip without an intentional delay. Now, when I say without an intentional delay, I don't mean it's going to go like in 2 cycles, right? Because what I'm about to tell you takes time. Because remember, I've got these wires that are connected, physical wires that are connected between these devices. And I'm actuating a voltage signal. So when what I'm about to tell you starts to occur, when the currents get high enough, there is a thought process that goes on. There is a microprocessor that has to make a decision. And anytime, anything, including you and me, when we have to think about something we are about to do, it's not instantly. There is a delay. So when you have a zone selective interlocking system and you tell that main overcurrent protective device to ignore its settings and trip without an intentional delay, for it to get to that point, it had to go through a thought process. And this is the thought process that occurs. Now, I'm going to ignore that. Let's talk about the zone of protection before I get into the process. No, I'm not. Let me do this. I'm not going to talk about the zone of protection. I want you to understand what. Okay, so let's start here. Let's talk about a fault that occurs anywhere downstream of this breaker. Okay, when that fault occurs downstream of that circuit breaker, the current that feeds that fault passes through the main overcurrent protective device and it passes through the feeder. So both the main overcurrent protective device and the feeder see current beyond the pickup points that you've already programmed. And I'll tell you what it triggers off of is the short time delay pickup point. And if you remember, I'll show you that trip curve and I'll show you that pickup point here. Just give me a second. When you've exceeded that trigger set point, what happens with the downstream device is it puts a voltage on those conductors that we talked about. That's what it does. It puts that 5 volts in one manufacturer's case across those conductors. The upstream main overcurrent device, when it sees that fault current goes above at that trigger set point, that trigger point, the first thing it does is it looks at that zone selective interlocking terminal and it says, do I see 5 volts there? If it sees 5 volts there, and we call that a restraining signal. If it sees 5 volts, do you know what it does? It trips. It will trip based upon the settings that you put in to its trip curve. So this main device, when it sees that current, it looks for the 5 volts. If the 5 volts is there, we call that a restraining signal. This device will trip based upon the time current characteristic curve, which is determined by the settings that you put into the trip unit. And if you put a 30 cycle delay, it's going to wait 30 cycles. If you put a 10 cycle delay, it's going to wait 10 cycles. If the fault current is high enough that it's in the instantaneous region of that main circuit breaker, it's going to trip instantaneously regardless of what you do. Right? If the fault current is high enough, it will trip based upon the trip curve. But if it's not in the instantaneous region, if it's in the short time delay region, it's going to look for that 5 volts. And if it sees the 5 volts, it knows that this breaker downstream is the one that is sending that signal. So what does that mean? That means both the downstream breaker and the upstream breaker see the fault current. And what does that mean? It means that the fault is downstream of both breakers. So when that is the case, both circuit breakers will trip based upon how they were programmed. And if somebody didn't program them, you could have the main trip before the feeder does, because they don't coordinate, because you've got an overlap in, say, the short time delay region or the long time region. Okay? If you did not program the set points in that device, in that pair of devices, they could erroneously trip. The upstream device could trip instead of the downstream, and you've not achieved your goals from a selective perspective. You may not have had any goals with regard to selectivity, which is then that's perfectly fine. But so that is case one. So the fault in case one, the fault is downstream of both breakers, and zone selective interlocking does nothing for you. It does nothing. What's going on in these breakers is they're going, okay, I see the upstream breaker, the main breaker says, hey, I see a fault. I look down, I see a signal, so that means the downstream device sees it too. I'm just going to sit here and wait and let these guys clear that fault. And the downstream device guy is going to go based upon his trip curve. And if he's got a 10 cycle or a 30 cycle delay, he's going to wait 30 cycles. Everything works the way it's programmed. Now, the next case, and that's basically what I'm saying there, the restraining signal, we call it a restraining signal, and it's a 5-volt signal. And remember, each manufacturer will use a different voltage, but the principles are exactly the same. Now, here is case 2, and this is when zone selective interlocking shines. When there is a fault internal to the distribution system, think about what's going on. There's a fault inside the panel board or switchboard or switchgear. Current is coming from the source through this main overcurrent. So this main overcurrent protected device sees the current, and it's above the trigger point. So what is its job? What is it going to do? It says, I'm not in the instantaneous region, because if it was in the instantaneous region, it would just trip. But I'm lower than my instantaneous pickup. I've exceeded my short time delay pickup. I'm in that sweet spot of current. And then what happens? It looks at the zone selective interlocking terminals, and it says, do I see 5 volts there? This is that brain process that I'm talking to you, that I told you about. So I see the fault. So you have to have time to at least sense the fault. And sometimes you might need at least one cycle of current, to be able to determine a value. Then you need to compare it with the data point, your trigger point, your short time delay setting. And then you got to say, okay, my fault current is greater than my pickup point. Now I got to look at those terminals and see, is there 5 volts there? So I have to sense that. And then that device is going to go, no, I'm not doing it, the device is doing it. So then that trip unit's going to go, okay, I don't see 5 volts there from the downstream device. Remember, this circuit breaker doesn't see the fault. There's no fault current flowing through it. It's happy. It's sitting there fat, dumb, and happy, like, hey, nothing going on that I know about. So it's not sending a restraining signal upstream. So the main breaker doesn't see 5 volts at that terminal. And then it makes a decision. It says, I'm going to ignore that time current characteristic curve. I'm going to ignore my delay settings. And now I'm going to trip. Now that process, if your circuit breaker in the instantaneous region had 2 cycles of trip time, when you add the process that I just told you about, looking for that 5 volts, sensing whether it's greater than the trigger short time delay pickup, looking for that 5 volts, and then telling that breaker to open. That adds some more. And in some cases, you're looking probably around 0.07 seconds of time. Which is still faster than, say, 30 cycles, right? Think about the reality there. So, and then, okay, and now why does time matter? Let's just talk about that. I want to help you understand why time matters. What do we know about incident energy? We know that I have an arcing current, and I calculate that arcing current based upon IEEE 1584. So I go in to IEEE 1584 based upon the available fault current, based upon the configuration of that equipment, the spacing of the electrodes and all that jazz. I calculate an arcing current. Then I go to my time current characteristic curve and I look for a clearing time. And I plug that into an equation, and that tells me the longer the clearing time, the higher the energy. So if I can reduce the clearing time, I can reduce the amount of damage that equipment will see. But the fault has to occur in what we call the zone of protection. So, if I have a fault, these are the zones of protection. The 2 red zones are outside of the zone of protection. If I have a fault on the main lugs of that main overcurrent protective device, zone selective interlocking does nothing for me. If I have a fault on the load side of the downstream circuit breakers, zone selective interlocking does nothing for me. My sweet spot is when the fault occurs in the zone of protection, in between the upstream overcurrent device and the downstream overcurrent protective device. That is the only time zone selective interlocking provides you value. Now you can nest these so that these downstream feeder devices here, this feeder device and that branch feeder device, and even maybe that device there, I could zone selectively interlock with a downstream piece of equipment, the next overcurrent device. And then I'm extending my zone of protection. But I would have to have those 5-volt signal wires connected external from this piece of equipment to the next downstream piece of equipment. And then obviously you get into the concerns of distance, right? If my next piece of equipment is, I don't know, 4 stories down, 4 levels down and over, then I got to think about, well, how long are my conductors going to be, and how am I going to route them there, and then is it cost effective to get that done? There might be other ways to achieve your goals. But the fact is that your protection, your faster clearing time, which reduces damage, only occurs when the fault is inside on the bus of that equipment. And there's your trip unit and that set point. So here is the set point right here. This is established as your trigger point because that set point controls this portion of the trip curve, whether it is left or right. That's what that dial does. It moves the curve left and right. It either has the trigger point higher or lower in amps. So the setting of that trip point will help you understand when that signal is being sent to the main overcurrent protective device, who's looking for the signal, the restraining signal, so that it just goes based upon the trip curve that you programmed into it, or maybe didn't program into it, right? We hope and pray that when the engineer does the coordination study or the selective coordination study and puts all of those set points inside of their study, that somebody is out in the field programming it. And hopefully an inspector is making sure that those numbers are right. It's simple, but it is something that's missed often. Okay, and that set point on that dial is going to move this portion of the curve left and right. And that pickup point, this pickup point, right for this curve right here, is what establishes the restraining signal, or when the main breaker is going to be looking for the restraining signal. Your current has to get high enough for zone selective interlocking to provide value. And that's why you have to do the proper calculations and make sure you set things correctly so that you reduce the amount of damage to the equipment. And like I said, this has been around for a long time. A long time. And we've been using zone selective interlocked systems to provide equipment protection for a very long time. Now, one of the challenges, let's think about the challenges in a zone selectively interlocked system, is to know that the system is working. We have trip units, we plug trip units, and we wire trip units together. But historically, there was no indication. So now, what we would typically do on installation, we would have a commissioning. And when we commission the equipment on installation, we would inject current. We would run a test to make sure that the devices are operating correctly and that they are wired correctly, or that they're wired at all. There's only one manufacturer on the market that actually has an indicating light that tells you zone selective interlocking is wired and functioning. Think about that. You walk up to a piece of equipment, there is nothing on that equipment that tells you this is a zone selectively interlocked system. There's nothing in the code that says it needs to be marked that it is a zone selectively interlocked system. In fact, the only place in the National Electrical Code that mentions zone selective interlocking is in 240.87. Section 240.87, arc flash reduction, and that section was put in for the electrical worker, and zone selective interlocking for circuit breakers is one of the options. So somehow, from an inspector's perspective, if you're using ZSI to meet the two requirements in 240.87, then you need to figure out a way to verify that that equipment was wired correctly. Now, the other good thing is that if you look at 240.87, one of the new sections that they put in there was that 240.87c has what they call, or what we call, performance testing. So just like in ground fault protection of equipment, when you install GFPE and you put ground fault protection of equipment on for the service, 230.95, I believe is the appropriate section for that. It will tell you need to test it on installation via primary current injection testing. That tests the CTs, make sure you have the right polarity. It tests the relay to make sure it will sense it, all that jazz. So item C, 240.87 Charlie, requires you to performance test your arc reduction technology that you used to meet this version of the code. And if you're doing zone selective interlocking, we have methods. We have methods to test it. And I'll show you, I believe I have that test, zone selective interlocking. I'm just looking here, hold on. Let me find it. Because I know, there we go. So for doing your performance testing, you're going to verify the equipment is functioning upon installation. And we put that in the code. We put it into the National Electrical Code because you want to make sure that when you install this equipment, it's functioning on installation. And we would rarely do this after the fact, check the CTs and things like that. So if you look at what the requirements are, you have to have all the CTs have to check for polarity. Make sure that what's marked in there, line and load or current goes this way, is not 100% correct every single time. So you need to check your polarity on the CTs. You're going to want to make sure the electronics are functioning. You're going to want to make sure that all of your sensors are working appropriately. Polarity, and I've had debates with various individuals on what level do you need to go to feel comfortable with the technology. Do you have to do a total burden test? All of that jazz. Maybe not. It's up to whoever is doing the testing. There's nothing in the code that says what test you have to do. There's just a line item that says you have to test this to make sure and verify it's working appropriately, and different individuals will go through different extents of testing. So you'll definitely want to know whether or not you have the right ratios and that the markings on the CTs are correct, and that's a simple test. Polarity, make sure that that little those little arrows are going in the right direction. Those have been mislabeled before. You can primary current injection test these, but I'll tell you also there are technologies that lets you do these without injecting current. So I'll show you the this is out of the performance testing for a manufacturer's solution. They'll tell you to ensure that all of the trip units have all the right settings. They'll tell you, they even show you how to open the case. And I'm sure they even show you how to plug it in, but this is a test set. So this is a test set that you can either acquire or you can get from the manufacturer of the overcurrent protected devices that you're seeing on the job site. I would say not that one manufacturer's test set may or may not work for the other manufacturer's equipment. So always consult the manufacturer to understand what you need to do to properly test that technology. So this is the box and whatnot that of the equipment. And we even show you have to plug it in. So you're going to need 120 volts source somewhere around there to do this test. Okay. So that's an important aspect of it. You'll need to plug there's a ZSI cable that will connect to the circuit breaker and plug into the test unit. There's the other end of that same conductor. One end goes into the test unit, the other goes into the plug or the test plug that's on the trip unit. And again, this is one manufacturer's solution. Every manufacturer, there's no standardization here, so each manufacturer will have their own method to get this done. Then you want to, in this case, turn the tester on to the on position. And then you have a screen that shows you all the different tests you can run. And if a zone selectively interlocked system can get complicated. Okay, it's in some cases it's not something that you if it's a nested system. Remember I was telling you, you could have a system that goes from your main service equipment down to another piece of equipment, down to another piece of equipment. You could have your main service equipment have a main configuration. So these systems can get quite complicated, and quite frankly, when you have like a main application, you've spent a lot of money on that equipment and you want to protect your asset. And you're going to protect that asset by putting technologies like this to work to minimize your damage, so you don't have to replace that equipment if there's an internal fault on the system. So the test configurations will these instructions walk you through, and you can pause this and read through each of these steps if you'd like, to make sure that you test those. So there are, again, many different configurations for zone selective interlocking. What I'm showing you right here, zone selective interlocking. I said that really fast. Did you catch that? I said zone selective interlocking. So this is a simple system. And one you might see on low voltage assemblies. You wouldn't see this on 120 volt systems or 240 volt systems. These are going to be low. You wouldn't see this in a panel board normally. You'll see these in low voltage assemblies and switchboards, the big expensive stuff, right? So you could have a main time main configuration. And when you're doing that, you need to simulate faults at various locations in this power distribution equipment. You can't just, you don't just test one set, because each of these circuit breakers has wires going back up to them. They think about it. You have all of these feeders down here, all of these devices have to be connected back up to the main, also back up to that device. And it's a complicated point method to get all the right wires in all the right spots. And you will want to, when you're putting this equipment in, this equipment probably is going to have other relays. It's going to have a lot of different technologies on it, and there will be a commissioning service. You're going to get someone probably from the factory of the manufacturer to come out, sit with a computer in front of that equipment and run through all the diagnostics and make sure everything is correctly wired and installed before you do what? Before you energize. Which, if you think about 70E, what does 70E tell us from a safe work practice? Is your first energization of this equipment, is that a normal operation? Heck no. It's not a normal operation. You need to dress when you start to energize this equipment. Think about how complex it is. And yes, we do all of our tests. We want to make sure we've crossed our T's and dotted our I's. And make sure we didn't cross our I's and dot our T's before we energize this equipment. It's a very important, critical piece of that pie. And the test equipment has to be able to accommodate that. That's why it's really critical that you speak with the manufacturer of whatever equipment it is that you're installing, and make sure that you're using the test equipment correctly, and make sure that you are testing the equipment on installation adequately to get that confidence level before you do what? Energize. Very important piece of the puzzle. Then you have test reports that will help you document the testing that you just did. Now remember, the test report's a critical piece of the pie because it's your level of documentation. It says what you did, how you did it, and all that jazz. These are all critical pieces that you need to document and make sure that you hand that over to your AHJ so that they understand the level of detail that you went to make sure that it was installed correctly. It's required by the code on installation. And then what that does, that sets you up so that later when you're following your 70B requirements and you have your maintenance plan built out, you don't have to go back and re-verify the polarity of the CT. You don't have to re-verify the arrows on the CTs to make sure the current is going in the right direction and that they were installed correctly, because you installed them the first time and you tested them on installation. Your follow-up continuing maintenance can be minimal as opposed to having to do all of that after the fact. All right, so summary. Zone selective interlocking is not a selective coordination tool. Zone selective interlocking is to minimize damage. It's been around since electronic trip units have been around. It has been around to provide protection for the electrical distribution equipment. It was employed for many years at your heavy industrials, who have the investment. That's what zone selective interlocking is. And remember, zone selective interlocking, you have downstream devices and upstream devices. It only provides a fast clearing time when the fault is in the zone of protection. Remember that. And if you're working in a piece of equipment, if you accidentally touch a load lug and you cause an arc flash there, zone selective interlocking does nothing for you. If you accidentally touch the line side of the upstream overcurrent device, the main in that equipment, zone selective interlocking does nothing for you. The fault has to be in the zone of protection. And what provides all of the protection when it goes off is the upstream main overcurrent protective device. That's the device that is going to ignore all those settings and trip without an intentional delay, which means what? Probably around 0.07 second clearing time, somewhere in that ballpark, which is a heck of a lot better than 30 cycles. A heck of a lot better than 30 cycles. That is what zone selective interlocking is there for. That's what it does for you. Where do you find it in the code? The only place you find it in the code is 24087. Will you find it in the field outside of 24087 requirements? Heck yes. Why? Because it's an effective way to reduce the damage in power distribution equipment, especially those big boys that cost a lot of money. Now, before I shut down, I want to remind you, next week, another Tech Tuesday, but we have a special event coming up in May, Electrical Safety Month, with Siemens. Siemens is going to be announcing a new solution, and you're going to hear about it here on this channel because we do that stuff. And if you're a manufacturer wants to come on a program, talk about the latest technologies that help save lives, help meet the code requirements, please reach out to IAEI. Send an email to IAEI and send me an email. Let me know, and we will get in contact with you and set up your IAEI News Live program. I'm looking forward to talking with each of you, especially those innovative manufacturers out there that want to share their solutions. That's what it's here for. Take an hour, let's talk. If you want to do less than an hour, all game. All you got to do is reach out. All right, so I hope you got something out of this session today. I'm recording this from the road, so this is not a live session. I had to pre-record this because I am actually doing a presentation working on some educational materials with another a group, and I was not able to do this one live, so I apologize for that, and hopefully you understand. All right, that's all I had. And I hope you, again, I hope you got something out of it. Thank you for tuning in. Thanks for what you do for the electrical industry. Thank you for what you do for IAEI and for electrical safety. Until the next week, I wish you well, God bless, and please stay safe and healthy. See you next week. Take care.